Okay, anything? You want to ask first?
When I go through areas,
Okay, chat.
yeah,
Okay, good. Ring means benzene ring, right?
kind of.
Can you describe why the arene sometimes is joined with 3 double bonds or
Okay.
and go through the addition?
Sure. Well, let's talk about
substitution.
let's talk about benzene first. Okay, benzene actually is a very interesting structure. Okay, now if you want to know benzene, right, you actually can learn from graphite first. Graphite, the structure, remember we have a hexagon honeycomb in there, right? Okay, so now interesting in graphite structure, right? All the carbon actually have 3 bonds only. Okay, but carbon actually is group 4. So therefore, in each carbon actually have a free electron. Okay, so if God lend you a scissors, okay, then you cut these things out, okay, and dip the things in the hydrogen. you might have actually you might have cyclohexane. Okay, or actually you have benzene ring. Okay, benzene ring. But what is a benzene ring, right? Last time, right, they
What's the question?
yeah, this is a mystery. Okay, so last time they think of benzene ring, they take it as a structure like this. Okay, last time, actually quite a long time they accept the benzene rings like that because they behave like this. Okay, but until that the technology of bonding, the bond length observations, right, is available, right? They go to check out the bond length. They realize that hey, the bond length for these 6 things, right? How come it's the same? First things, because it should be different. Double bond should be closer than a single bond. Okay. So secondly is that they find how come the length itself is in between of a double bond and a single bond. So that is why they got to think about something to propose. Okay. So what happened is that they could observe benzene structure in 3 dimensions, and then they realize, right? Now, first thing is that if they use the, remember last time they haven't have a new structure yet, they stick to the old structure. Okay, when you stick to the old structure, right, what is the hybridization of this carbon here?
SB3.
Nope.
Okay.
SP2.
SP2. Okay, because 1 sigma, 2 sigma, and 3 sigma, right? Okay, 3 sigma, SP2. Okay, so you need the SP2 hybridized bond. So this is why the 4th one, right, is actually a pi bond. Pi bond are made up of pi bond are normally made up of p orbitals, okay, and then connected in this way. Okay, okay. So therefore, right, in 3D visualizations, right, if I draw a little bit horizontal, okay, the so-called double bond is formed from a p orbital with p orbital in this way, overlap. Okay, and you can imagine that this one and this one overlap, and this one and this one overlap. Okay, so this is why I give you the double bond, double bond, double bond here, and this kind of double bond, right, is still this kind of thing overlap. But the 6 of them are so close in such a way that even though they overlap, okay, I just draw the top one here. It seems like not, they're so close until when they overlap together, the 6 of them, right, they're all partially overlap in 3D model. Okay, so this is why, right, this is the latest model. Okay, this is the ancient model. Okay, but in between the latest model and the ancient model, because the latest model used the 3D observation to realize the 6 p orbital when they're so close together, actually they all overlap a little bit. Not fully overlap to be a covalent bond, but it is overlap enough to have some sharing of electrons. Okay, so this is why they call all these things at 1.5 bond now. Okay, but before these observations, right, they say that because the benzene ring, okay, is having a double bond. A double bond means consists of 2 electrons in this way. Okay, so there will be one instance, right? This electron will just come to here to form double bond. Okay, because it's actually at the same place, don't even have to move. Okay, now last time they don't have the 3D visualization. They say this sometime will move together, and then this move together, this will form this structure. Okay, and when sometimes these three move together, get this structure. Okay, so therefore, right, you have a very busy structure about a benzene ring like this, and interchange with this. Okay, in a very fast speed, keep swapping. Okay, and once you have keep swapping, right, that means virtually, right, and actually how they swap is just that this guy is at here, this guy is at here, but they're actually the same place. Okay, a little bit left, right, left, right, left, right, left. Then this one a bit left, left, right, left, right, left, right, left. Then 6 of them are actually all a bit left, right, left, right. Actually, they didn't move at all. Okay, so this is why they call this two extreme case a resonance structure. So they virtually stay at the 1.5 or in between positions. Okay, so actually we accept the latest model says that they are actually partially overlapped. Okay, so therefore, fussy people will just say that okay, benzene now is written this way. The ring means that inside should have three pi bond, but they don't know where it is. It can be here, 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 or here, 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 at any instance.
So they are moving electrons.
Yes. So what's so interesting about benzene ring, right, is that when they have these resonance structures, right, actually they have a spin in. So that when the cloud is in this way, right, okay, actually they have a spin in this way, the electrons. Okay, or an R way, I don't know, okay, I mean, it can be clockwise or can be anti-clockwise, but they're spinning in a circle. That means, right, when the time we come to here is the electron hop to here, and the time we come to here, electron keep hopping. The 6 of them actually keep rotating inside the benzene ring. This is why they give a good circle. Okay, so when they keep spinning, right? Okay, but this is not chemistry. Okay, when they keep spinning, you will have a current. Electron movement. If the electron movement in this way, a current is in this way, right? And when you have a current this way, right, use one-hand grip rule. Okay, a magnetic field, right, will come out of the paper. Okay, now remember last time Sec 4 we talked about it is dangerous to switch on or switch off a large electromagnet, right? Because the inductance, okay, the inductance will keep, when you try to switch on, but the inductance will keep the circuit switched on. So this is why, right, if you open the circuit at the time, and you open up the time, okay, the inductance will try to keep having current flow. So this is why the electron will fly through the air, so it will have spark. Okay. On the other hand, we say that sometimes when you switch on, you refuse to switch on. Later, they suddenly switch on. It's due to inductance, right? We have this word, right? And what is inductance? Inductance, right, is actually this phenomenon. It's called electric inertia. Okay, heard of what's the inertia? Right?
Moving,
Yeah. So the idea is that what's the meaning of inertia? Inertia is like you want to move, you refuse for you to move. But when you want to stop, we will refuse for you to stop. The reason why is because when you have a current, you generate a magnetic field. Once at the instant that you break the current, but the magnetic field is still there at the time, right? The magnetic field would want to try to get the current back. Because current will induce magnetic field, but the magnetic field will induce back a current. Okay? So when you have current at the time, no magnetic field at the time, the magnetic field will start to get generated. But when the magnetic field is generated at the time, you try to break the current, the existing magnetic field will try to get back the circuit. Okay? So this is why, right, the benzene ring structure of this kind of spinning, right, will give you electric inertia, okay, that you cannot stop the current. cannot stop the spinning. Okay, so what is it to do with chemistry? Is that benzene ring, right, have a very interesting structure. Okay, but if you want to really see what happened, right, use the old structure. Okay, use the old structure. It's easier to see. But when you draw, please draw the new structure. Okay, so what happened is that you have one of the example as electrophile, but you need Cr plus, right? Very strong electrophile to attack benzene ring. Okay, so what happened is that when you have 6 hydrogen here, okay, I don't draw a rest. Okay, so when it come to here, you try to get the double bond, right? When you try to get the double bond, the 2 electrons all go up to the Cl, so Cl no more plus. But on the other hand, right, the carbon here will be carbon positive. Okay, so this one you have a carbon positive, and you have 2 bonds here left. Okay, so at this instance, right, when they can attack in because benzene ring is electron rich. Okay, but once it comes to attack to you, right, it breaks the circuit inside. Once you break the circuit inside, right, the magnetic field that induced, right, actually try to maintain the circuit. So this is why you straight away kick out one guy and give back the benzene ring. Okay, so this is why benzene ring is so strong in such a way that it doesn't like to get opened up. If it's temporarily get opened up, the double bond, okay, you try to do everything to get back the double bond, get back the benzene ring. Okay, so this is why benzene ring is very stable, because of the magnetic field, right, will have to refuse to change the electronic configuration. Okay, but that's totally a piece of extra information. Okay, but just to let you know that benzene ring is stable because of this reason. But on the other hand, benzene ring is very attractive because you have a lot of electrons inside. Okay, attractive yet stable. It will attract things over, but you will not let it to react much. That's the So this is why when in the temporary state, right, in the temporary state that this Cl or Br plug in, right, you break the circuit, you have a H and Cl or Br there.
They have like when the Cl plug into one carbon, so that carbon is temporarily sp3.
Temporary sp3, you're right.
Yeah,
temporary sp3.
And then so because they don't want to be sp3, so they
No,
kind of
they want back the circuit inside.
they want back. Also, they want that carbon to have to make the
it's
double
like,
bond.
it's like once you
carbon.
come in here, right, this ring, right, is broken halfway because you don't have double bond anymore.
Then you'll kick out one.
Then
Kick out carbon,
then it's not yet kicked out. You have Cl and H there inside, okay. But the magnetic field, right, try to continue the circuit, so we will want to get back the electron back to here. So just now this electron swing to here, so we ask this guy to give back the electron. So weaker one, right, come back to supplement this, and this guy gonna leave.
Oh, the H comes in.
Okay, it's the H come out. Okay, so the idea is that even if you have double bond, it doesn't quite go additions. If because in the intermediate step you add into it, okay, you try to get back the double bond. Okay, because of those inertia things. This is interesting thing about benzene. Okay.
So that hydrogen give away that electron, so it gets kicked out of the structure, so it become a hydrogen positive.
You're right. Okay, because the electron got snatched by the benzene ring back. Okay, so that guy become poor. Okay, now so benzene ring, right? Once you understand this structure, benzene ring, you need to know first one, it is electron rich. Okay, very rich. Second things you need to know, right? Benzene ring, it is relatively very stable. Okay. Okay, stable as in it will not go much about the. Okay, only temporarily you can disturb that. Okay, it's very rare that you open it up. Temporary reactive. Okay. Thirdly, right, it is asymmetrical, very symmetrical. Okay. Symmetrical makes you sometimes when you want to attack, also don't know where to attack. Okay. Now, but in any instant you need to know. Okay. If you have anything that can disturb the symmetry of a benzene, right, then you break the symmetrical nature. Then you may also make it not so stable. That means it can be very reactive.
That's temporary.
Temporary reactive. Okay, that means in the intermediate step you can have benzene ring destroy. Okay, but you will get back benzene ring. I'm not talking about the whole compound. I'm just talking about only this ring only. Okay, this ring is stable, doesn't mean that everything is stable, okay? Okay, now, so this is why the first thing is that if you want to just react purely with benzene ring, okay, firstly, if you want to react with benzene ring, okay, the first thing is that you need an electrophile, of course. Okay, you need electrophile. Okay, because it's electron rich anyway. Okay, secondly, right, there should be no additions normally, unless in extreme case it's a substitutions. Okay. Thirdly is that if you just want to have symmetrical benzene ring, you need a strong electrophile.
If you need a what?
You need a strong electrophile. Sorry?
You need a what for a strong electrophile?
You need a strong electrophile.
Do
If you
what?
want to do the business with a symmetrical benzene ring.
Oh.
Can. Okay?
You need a strong electrophile to react with a benzene.
Yes. And benzene rings, right, have two
Strong halogen, is it?
not really. You need something ridiculous. For example, you need a Cl plus. Cl left to be minus, you make it plus some more. Okay? Cl is already unstable, you make Cl plus is even unstable. Right? It doesn't make sense. And NO2 is NO2, right, by nature is actually called a nitrite ion. Nitrite ion, okay? It's left to be NO2 minus. And then they go to generate something, you want to wear benzene ring, you will generate an NO2 plus.
How they generate?
Use the displacement reaction concept. A stronger acid and displacement we call it from the salt. Okay. I'm sorry. Yeah. A stronger alkaline displacement we come from salt, stronger metal displacement we come from salt, and stronger non-metal displacement we come from salt. So that when you have H2SO4, a stronger acid, where with a weaker one.
HNO3.
Now, so this one, right, will be forced to behave as if it is like alkaline. So if you think this got to be alkaline, how do you make it looks like alkaline? Alkaline is OH minus, right? Okay. So play the number games. You know the plus side got to be NO2 plus.
Oh.
Then you see how come you can generate NO2 plus, right? Because a strong acid will force this guy become alkaline, even though this is acid. Okay, so the H plus will have an OH minus here, and then you have NO2 plus there. Of course, you have
You
the
mean
H.
you put two acids together, they will react?
Sorry?
You
Yeah,
put two acids
you're right.
together.
That's how you do the nitrations, right? Make a nitrobenzene. Okay, that's how you do it.
Oh, so this is something like the catalyst.
Not really. It's a generator of the new electrophile.
For aromatic
Number 2 is strong.
substitution.
Number 2 is cross addition.
That means no additions. No additions. Okay, no additions. Okay.
For benzene,
You have substitutions.
for benzene reactions, you don't need any catalyst.
It's up to you to talk about whether
is
it's
it?
no. It is a catalyst.
No, this here the FeBr3 or FeCl.
Yes.
What is this?
This you can say that it's a catalyst because without it, right, the reaction will go very slow. Okay,
Why
and
it goes slow?
because they need to generate something weird. It's something like Cl plus.
So the Fe something generates that weird thing.
You're right. Okay, so they are actually electrophile generator. You can still call them a catalyst if you want to. Okay. So the point is that how to generate a positive electrophile. Okay, you need some strong one. But if it is non-symmetrical benzene, you don't need all this. Okay. So the first one, just like I say, the first one you can generate is NO2 plus, okay, which is made by H2SO4 concentrated, okay, with dilute nitric acid. Okay, these two together will generate NO2 plus. The second one is the halogen plus. Okay, halogen plus you need a Lewis acid or halogenal carrier, right?
Lewis acid catalyst, they call it.
Yeah, Lewis acid. They call it Lewis acid, or they call it a halogenal carrier. Okay, be careful. Okay, sometimes they use a halogenal carrier in the question. They mean the same thing. So how does this work? Is that
With a metal, Fe or Al.
yeah, but more than that, you can use you can use lead. Yeah, or something. Anyway, if I'm not wrong, it's Fe.
FeBr3, FeCl3.
Yeah, Cl3, right? FeCl3.
Yeah.
I think they won't use Br3. They use Cl3. Even
they say Fe and Al, Br and Cl are interchangeable.
Fe and Br is it?
Fe and Al, iron 3 plus and aluminium 3 plus, these two metals are interchangeable. For
Yes.
This.
The idea is that so what is the halogenal carrier is that it have actually have this FeBr, right? Br3 and ALX3 anyway, all these things, right? ALX3 is easier to explain. ALX3, right? We know that it is AL will be Cl, I think. AL will be Cl.
Yeah, AlCl.
AL will be Cl. Okay. I don't think AL can be Br.
Ah.
Yes. AL with Br will not be covalent bond because AL with Cl will be covalent bond. Now, so AlCl3, right, is actually a covalent compound in this way. Okay? And then you have an empty orbital here.
They thought they would form the Al2Cl6.
Yes, if you have two of them, okay, under high pressure, but let's say under low pressure it will not. Okay? So what happened is that this case, right, this is electronegative, electron drawing, right? And this is electron drawing, or this is electron drawing also. Everybody is electron drawing. So this is a very good Lewis axis. Yeah, actually it's very strong to pull anything to fill up these two places. So when you have X2 here, okay?
What is X2?
Cl2, Br2, whatsoever 2 there.
Oh, so you need Lewis, so you need this type of like ion plus a halogen.
Yep, Al is a good choice because it's a covalent compound. Okay, so once you come this double bond, right? Sorry, this two electron, a single covalent bond, right, will get snatched into here. Okay, so when it's snatched into here, right, you can treat it as if it is a minus and a plus, and the whole minus will plug into here. So they become Al, Cl, 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 and X minus. Okay, and then you generate an X plus here. Okay, and the X plus, right, will be the electrophile.
How do you call the X answer?
Any halogen. Cl2, Br2, okay, those kind of things.
Oh yeah, can I call you back in like 1.5 hours time, busy now. Thank you. Who the hell is that? Say return call.
Okay, so for Fe, how it works, right, is actually working the same thing because Fe is the transition elements. So you have a lot of empty orbitals. Okay, so the empty orbitals you have, right, will just kidnap the covalent bond here. Okay, will also be the same. Okay, but you can't draw because it's not octet. Okay, Fe have many empty orbitals. Okay, but why not just Fe metal? Okay, it's because Fe itself is not electronegative enough. Even though you have a lot of empty orbitals, it will not, by nature, it will not keep pulling the electrons, so it will not be helpful. So this is why the Fe, right, needs a few chlorine around it to help to pull the electrons.
Fe for Br also can, right?
Yeah, Fe for Br also can. Okay, so the Fe case is just that they need someone to help him to pull the electrons. So that make the Fe empty orbitals, right, is a more reactive sign. Okay, therefore we pull away your covalent bond, your X plus will come out. Okay, now. So this is the way to handle symmetrical benzene. Okay, you need this kind of halogenal carrier or Lewis axis.
I got a question.
Yeah?
For the X, right? The X, must it be the same halogen as?
No need.
Anything works?
No need. Yes, anything works. Okay, normally it work for, guaranteed it work for chlorine.
Chlorine and bromine.
Bromine, yes, bromine also can, yeah.
But it can also be same, right?
But you can have YX. Okay, I will tell you this. Okay, it can also be the same, of course. Okay, the BR you can use the
So you can
BRC
put any halo.
yeah, you put any hydrogen, yes. Sometimes you can use something BR with the chlorine Cl in the Lewis acid, they also can. Okay, now, so the point is that the trick is this. Okay, so to tackle benzene, right, because you don't only see benzene, you see benzene ring with many things. Sometimes you see a NO2, right? Okay. Sometimes you see a NH2. Sometimes you see a CH3. Sometimes you see a chlorine. Okay.
Actually,
So this one now you know. This one now you know. This one later you know. This one I told you already. Okay. So how to do the CH3? Actually, it's the same concept because they just need to replace the Y by CH3 too.
so it's like CH3 plus
CH3 chlorine.
CO.
Okay, or CH3 bromine. And then with the Lewis axis, right, the bromine will get snatched into it. And then you generate a CH3 plus. The CH3 plus will do the benzene ring. Okay, so if you want to plug anything, generally use the Lewis axis plus your anything X. Okay, then the anything can be plugged into the benzene ring. Okay, but of course, make sure anything will not be more electronegative than the X. Okay.
If not, with anything
Yeah.
beside.
Instead of X plus will go into it. Okay. Easy? It's not that hard. Okay, so now we keep talking about symmetrical benzene ring, right? So let's talk about so when benzene ring react, right, what are the requirement and what happens when it's not symmetrical? Okay, the first things, right, you need to know the stability. I don't know why they don't teach all these things, right? Stability of benzene ring. Okay, it's due to two factors. The first factor is the richness of electrons. Okay, more rich, more reactive, less stable. Okay. The second one, right, is the symmetry.
They say what high bond form as a result of collateral overlap of unhybridized p orbitals.
Yeah. Just now I showed you the 3 dimensions, the dumbbell, right? They are actually 6p orbital, and these 6p orbital are not hybridized bond, right? It's the pi bond, right? So actually when they're too close, actually they all overlap one halfway. So that's why they give
So that's
you.
why it is stable.
Yeah, that's why they give you that channel of electron spinning, okay, and give you all those.
So this is the reason
magnetic
why
fields.
it's stable. Also one of the reason.
Not really. The reason is because they channel up, but the reason after they channel up, how come channel up means more stable? Okay, it's because of the magnetic things, but those things are not chemistry, so they don't mention much. Okay, so explain until they all share like a very good lattice that it's very hard to break. Okay, that's good enough. Okay, don't go so deep.
What's B?
Sorry, the B is a symmetry. Okay, whether it's symmetrical or not. Okay.
If it's not symmetrical, why will it react?
That means if it's not symmetrical, right, it will be more reactive.
This is the reason for stability of benzene.
Yeah, factors.
Oh.
Factors or reactivity of
If it's not
benzene.
stable, means it has more like weird electrons or something.
Now, so if you want a very reactive benzene ring, you need to be electron rich, richer than the symmetrical one. Make it even more rich. Okay, and not symmetrical. Okay, if you want a very stable benzene ring, that means you just use a plain benzene ring, or you take away some electrons somewhere. Okay, then you
Why
make
does it
it.
have a lot of electrons? They have like 6.
Yeah.
6 is a lot.
Sorry.
They have like
Okay,
6
sorry.
electrons flowing.
Yeah, you're right. Okay, but let's change this word to a better one. Hey, richness of negativeness. Okay, I think this is better. Okay, but make it more abstract because the number of electrons is fixed here. You can't change it. Okay, but if with different elements tag along next to the benzene ring, right, you can make the benzene ring more or less negativeness. For example, if you have a group which is electron donating, okay, a group with electron withdrawal, but it will not take away the electron, but will make the negativeness richer or less rich. Okay,
But
now
mostly mostly it's electrophiles that react. So it will lower
Yeah.
the benzene's
Example,
negative.
if you have a chlorine here,
Yeah,
a benzene replacing a hydrogen with chlorine
I kind of like suck the
Okay, now
electron.
so will other carbon side, right, be more reactive than a plain benzene ring or less reactive than plain benzene ring? Okay, so compare this with this. Would this be more reactive or will this be more reactive? The answer is this is more reactive. Okay, because chlorine is electron withdrawing, therefore it will make the benzene ring less electron rich. Okay, therefore the rest of the side is less reactive than this. Okay, but on the other hand, if you have a CH3 groups, this is electron donating. Okay, so this is why it makes the benzene ring even more reactive. Okay, now so-
CH3 is electron
donating. R group, all the alkyl group is electron donating. Now electron donating you found is very weird. How come carbon is going forward while electron donating, right? Okay, the idea is that is not due to carbon, it's due to the 3 hydrogen activity.
I think
Okay, the H is electron donating and carbon will not withhold the donated electron, so this is why it is electron donating. Okay, if this center atom is electron withdrawing also, they will keep whatever you donated, so that it will not be electron donating. Okay,
so carbon doesn't really care but
carbon is like, yeah, it's like I don't get and I don't push also. So if other people push to me, right, I will try to push also. Okay. So chlorine is interesting. Chlorine is itself electron rich. I got so many lone pair, but he is very, what do I say?
greedy.
Yeah, very just don't want to spend. So the electron, so when you tag along with it, right, this make it even electron withdrawing than the donating, even though he's rich, he's stingy. Okay. So something like that. Okay, but anyway, let's come back to this. Okay, this the stability of or reactivity of benzene ring, right, is due to the richness of the negativeness. Okay, and whether it's symmetrical or not. Okay, now in these two factors, right, this is the dominant factor. So the first one is dominant factor. The second one is that means if you say I destroy the symmetry, but I make it less electron rich, that means I take away some negativeness. In overall, we'll make it reactive or not reactive. Okay, the idea is that we'll make it more stable, that means not reactive, because this factor is a dominant factor. And
More
this is the second factor.
negative it is, more
Electron.
stable it is.
No, more negative means more reactive because electron rich, right?
But this because it is electron rich, so
So therefore you attract the electrophile, right? So more rich means that it's easier to attract the electrophile.
more
Okay.
negative.
Yeah. Or I should say reactivity of benzene instead of confusing you. Okay. But then it will be don't balik, it's not symmetry, it's become asymmetry already. Okay, whatever it is, okay, so this is the two factor, okay? The two factor is that how rich it is and how symmetrical it is. Okay. So let's talk about the
So
orange.
when it's more symmetrical, it is more stable.
When it's more symmetrical, it's more stable. When it's more symmetrical, it is more stable. You're right. Yeah. Okay. So imagine that if I have
Because it's stable, it's harder to break the thing.
yep. Okay. You're right. Okay. So this versus it's very hard to illustrate in this way. But if you have one guy, Corey is a bad example because he do things on the other way around. Okay. The idea is that if it's a benzene ring, right? Yeah, actually, I think you kick out the second factor. Don't care about it, okay? Because it will just divide by one thing, the first one. Anyway, in here, right, the six side, okay, they are exactly symmetrical in a positive negativeness. So if I have an electrophile want to go somewhere, the six side to him, right, is all the same.
So it randomly takes one.
So it might not easily get a spot and go to coin. It may keep follow the electrons, keep spinning. Okay.
Oh.
Okay. So, but if you have one, let's say CH3 here, okay, you make it electron rich here because electron donating, right?
So there is more electron rich.
Yeah,
than
but
the
once you have a negative here,
other
right,
sides.
this is what we induce. You induce a positive here, and a negative here, and a positive here.
Oh, so all the negative sides we want to sum.
Yep. Okay. Am I correct? Oh, I'm wrong. No, sorry. When this positiveness come, electron donating here, it donate all the way to the N junctions here. It's here. Or the other way around. Okay, these 6 things are always done by 1. Okay, so it actually help you to enhance these 3 sharp point for substitution.
Where is donating, it goes
It's donating,
through
yeah.
the all the way
Goes
there.
all this, yeah. Okay, so for the detail, right, there are some general rule, but there are some specific cases also. So in your syllabus, they only take out 4 or
Is
5.
this one?
There's one, so what 2, 4, 6 directive and 3, 5 directive, right? Have you heard of that?
Don't have.
Okay, right. Okay, never mind. Okay, I'll take everything here, and your school will tell you again in some other chapter when time we talk about asymmetrical benzene maybe. Now, okay, I'll rub this. Okay, when you have a benzene, right? Okay, we talk about what happened when you have something tag along with benzene. Tag along with benzene, okay? Then we got to think about what happened to the benzene ring, okay? And what happened to this group, okay? Benzene will have an effect on the branch, and the branch will have the effect on benzene ring also, okay? So let's talk about what branch can affect the benzene ring first. Okay. Now, for reactivity, it's very simple. All you need to see is that do I have a lone pair next to it? Okay. Lone pair. Yes, lone pair. Lone pair. That's bad. A lone pair. Okay, fine. Exceptional case. Okay. So whether a group is electron donating to a benzene ring, you can justify by whether the next element, the next atom, okay, has lone pair or not. Okay, if yes, electron donating. If no, electron withdrawing. Except one guy. Okay, electron donating, yes, except halogens. So chlorine, one example, bromine is better. Okay, that means chlorine, even though have lone pair, it is considered as the electron electron withdrawing. Okay, but on the other hand, right, for no lone pair, it is electron withdrawing. Okay, withdrawing.
Don't have a lone pair.
Yeah,
Something
but
like
except this guy,
metal.
which is a CH3. Yeah. Okay, which
But
is
metal is
it doesn't have a lone pair, right?
metal is a nucleophile.
It's not about nucleophile. That means when you already bonded with benzene, what is this R affecting the benzene ring?
Oh.
This is the rule. Okay, this one is homogeneous. Okay, so you have a lot of examples. The first one, they have phenol. Okay, the second one, you have is chlorine. Third one, you have is nitro. The fourth one, you can have phenylamine, and then you have ester, and then
You see the direct next element.
yes, it's the direct next element. Okay, CH3. Okay, or CH2, CH3. Okay, let's have CH2 and CH3. Okay, now, so which one is electron? Which groups, right, to the benzene ring is electron withdrawing and which one is electron donating? Okay, this one,
Withdrawing.
no, it's donating.
But
It have
you have
lone pair, right?
you have lone pair what?
Yeah, if a lone pair means donating.
Oh yeah.
Lone pair means donating, so make it
Oh.
activated. The ring get activated. Okay, so this one
This one
is an exceptional case. Okay, so
withdrawing.
withdrawing. Okay, this one,
This one got lone pair or not?
You got to be careful, okay? So and O2, so maybe double bond. Or cannot have double bond.
This one is
O2.
additive bond.
I think like that. Make sense? 1, 2, 3, and 4, 5, right? Okay, nitrogen 5. Okay.
Then they don't have a lone pair.
Yes. So this is withdrawal. Okay. This one?
This one should. This one got a one lone pair, so it's donating.
Yes, it's donating. You're right. This one?
This one no lone pair.
So it's withdrawing. Yeah, you're right. Last one?
This one withdrawing also.
Donating. Exceptional case.
This is not this is H2
Yes. Okay. So pardon me. It's all alkyl group.
Oh.
Just help me a bit. All alkyl group. Okay. Can? Understand? Now this is very important. Okay, very important. Because when you have electron donating group, the ring get activated.
Ring
What
activated.
The benzene ring get activated. Okay.
It's already very stable.
So now we are unstable already.
When
Activated, right?
When
When
it's
you add electrons in.
When you add electron donating group, right? You make the ring, the
more
benzene
negative.
ring, very reactive. Yep. More negative means more electron rich, right? And it make it unsymmetrical now. Okay. So this is why this will all increase the reactivity of the benzene ring. And when you need to do any additions like benzene ring, right? Under this kind of benzene 1, 2, 3, right? You don't need to use Lewis acid. Don't need to use halogen carrier. Just pour your Br2, okay, in. You will get 1 to 3 substitutions, one shot.
Oh.
Okay, it depends on how crazy that the ring get activated. Okay, so you don't need halogen carrier. This benzene ring will help you to behave like halogen carrier, pull the guy out. Okay. So remember this, okay, electron. Which one is electron donating? So this is the rule. Wait, lie, sing lie. I need your eyes. Okay, 别睡觉, right? Okay. Now, learn two things here. Now, this is the first thing, very important thing for you to know. Second thing is that if you have things attack now, so what happened to the withdrawing group? Okay, you may need to generate an even higher concentration of your electrophile.
If it's withdrawing, then it will induce negative to other sides.
Yeah, but on the other hand, you make the whole ring positive. Okay, make the ring positive, right? That means it's not so favorable for electrophile. So you need to generate a lot of electrophile to go to attack. Okay, or generate some which is more extreme electrophile to
So
attack.
you only want to attach one.
Sorry? Yeah, you need higher concentration.
No,
That's
as
what
in you want to attach one to one benzene only.
Yeah. Okay. Yes.
Then if it's already attached, then.
No, I mean, if you want to attach another one.
But I thought you only need to attach one.
No. Okay. Later you need to learn a lot of phenols reactions, phenylamine reactions, and all these things. Okay. That means you already have a group, right? What happened to the second group? It is very important, okay? Because the third one is talk about orientation. Okay. So if they react, right, which position will you react? Okay. Again, right, there's another two rules for it. And there's two exceptional cases also. I hate it. Okay, if this is electron donating group,
You haven't complete your sentence just now.
sorry, say again.
If you already attach an electrophile, then what do we do? Make it more negative.
Make it more negative. Electrophile.
We attach.
No, I mean that if the benzene ring already have a group text to it,
And it's withdrawing, then
and
you
it's
must make it
withdrawing.
more negative.
If you want to attack other positions, like how you react with benzene ring, right? You need more harsh conditions, because
Like
the
what?
ring get more stable. Like you need a higher concentration of your electrophile. Okay, you need to generate more that kind of things, or in a higher temperature that kind of things. Okay, or generate a more ridiculous electrophile.
Actually, I like here only. After we find out whether the R group that you attach is electron donating or electron withdrawing. So if it is electron donating, so it will be more negative, so it's more reactive.
The ring is more reactive. That means the rest of position is more reactive.
But that position is not reactive.
That means now after you check this group, this thing cannot do anything anymore. Okay. Anyway,
Oh.
when we talk about the ring is more reactive, means that the rest of the side is more reactive. Okay. We talk about the rest of the side. Okay, the 5 of them. If you want to do the same thing, like you put a BR there. In these 3 cases, you don't need a Lewis acid carrier. You can just chuck the BR there.
To attract other electrophiles.
To attract.
Make it more reactive to attract other electrophiles.
Yeah.
But
Now this group can no longer react. Okay. So don't worry about it. Okay. We'll talk about if you want to do a substitution at the rest of the side.
the benzene ring can only attract electrophiles, right?
Yeah. It's actually electrophile. Yep, you're right. Okay, so this one.
CH3 initially is an electrophile.
CH3.
The donating one.
CH. This one. Yeah, it's no. This one after you plug in, right, you don't care about whether it's electrophile anymore. It's already part of the benzene ring.
Then
This guy is not going to react this again. I'm just saying that.
Initially it's an electrophile, but after attaching you will donate.
After attaching, yeah, it will be an electron donating group. Nothing to do with the electrophile. It's once you park into it, right, you will see this structure, what is this effect. Okay.
So before you attach likes electron, after you attach
Yeah.
to dispel.
Not like the spell, it will donate the positiveness to it. But it will donate the negativeness into it. Because they have no relationship. Whether before reaction is the electrophile. The electrophile is not in this structure.
Oh, there's no relation. Okay.
Yeah, the electrophile have charge, this guy don't have charge, this kind of thing. Okay, so they are no relationship. Okay, that means if you start like this kind of structure, okay, what will happen or what is the things needed for you to substitute in the rest of positions? Okay, that's the more requirement or less requirement. Okay, now this one you need to know because you need to synthesize the different groups in different positions. Okay, we have general things you say that if there's an electron donating group.
If a electron donating group is plugged inside the benzene.
Yep. Then
We don't do anything really.
then the substitution positions, right, will be 2, 4, 6 positions.
Counting the
Otherwise, right?
original substitution and one.
No, yeah, the original one is called 1. Okay. Otherwise, right, the position substitution would be 3, 5. That's what you need to know. Okay. 2, 4, 6, and 3, 5.
If an electron donating group is plugged into a benzene,
Then
so it will induce negativeness at number 4.
at 2, 4, 6, 3 positions. Okay, number 4 first, you're right. Okay, but the number 4 right now, for example, this one, right?
Yeah,
Now what happens is
to
that
number 4.
it shifts to number 4.
Then
So
all the neighbors are positive. Right?
yes, and then the positive neighbor becomes negative.
Okay.
This how come is 2, 4, 6.
Okay.
Okay, this one, these 3 positions will be
But
favorable.
this
for-
theory very hard to write down.
No, this one don't need. Okay, you don't require. Okay, you just need to tell them it is 2, 4, 6. Okay, they will just check you which position it is, and when you substitute this one first, and then after that that one first substitute with this one, right? You have different structure. For example, you get a chlorine in before you get a nitro, get a alkyl group in. The structure will be different from getting an alkyl group in, then you get chlorine go in. Okay, I'll show this to you in a minute of time. Okay, remember if it's electron withdrawing, it will be 3, 5 directive. Okay.
What's the theory behind if it's electron withdrawing?
Now this is electron withdrawing, right? What will happen is that it will pull the opposite one into here. Okay, so this one is make it positive. So this negative, negative, positive, positive, and negative. Okay, so this two will be favorable for electrophilic additions. Okay, it's not. It won't really go to positive. It's relatively more positive than the rest. It's still electron rich at few positions. Okay. Okay. Okay, you don't need to explain it this way. It is totally not serious. Okay. But you just need to know that 246 and 35. Okay. How do you know which one 246, which one is 35? Just like that. Okay. Now,
Then those positive ends will attract the nucleophile.
no, it won't. Because remember, the positive here is not really positive. The positive is relative to the neighbor, it's a little bit positive. The whole ring is always electron rich.
Okay.
Yeah. Okay. Okay. Now, so what is this used for?
To plug certain stuff into certain
Yeah,
position.
let's try. If you plug a Cl, then you plug a CH3. Compared to you plug CH3 first, then you plug Cl.
You'll be different.
It will be very
positions.
different. Yep. Okay, enjoy molecule. Okay, benzene ring, I use a Lewis axis plug a Cl there. Benzene rings, I use the CH3Cl with a Lewis axis and plug a Cl there. CH3 there. Okay. Okay, done. Okay, so these two things come out
What's the difference?
separately.
To plug, you plug different thing, but you use the same.
No, the first one I use a Cl with the aluminum ALCl3. This and this one I just need to use this one with ALCl3. Okay, then you get plug. It will just give you the correct one. Now then, the second step is that okay, this is electron withdrawing group. This is electron donating group. So when I plug a Cl there, I do not need the hydrogen carrier. I straight away pour my Cl here and go in. Okay. But this one is electron withdrawing group. So of course, when you want to plug in a CH3 group at a time, right, you need a higher concentration of this with the ALCl3. So condition wise, right, because this is electron donating, so make the ring activated. So you can just use whatever you want. The benzene ring will help you to tear the electrophile inside. Okay. So what will happen is that because of benzene ring, this will split to Cl plus, Cl minus, and then this one can go in. Okay.
So I'm going to kick a hydrogen out.
Yep, now this one, if you have high concentration of this, right, you will anyway get this, but slowly you will react anyway. So now, if this guy go into here, go into which positions? It is 3-5 directive, so you have the things going this way. Okay? But if the Cl plus in here go in, right, it will go in 2, 4, 6 direction, so it will go in this way or this way. Okay? Either one here. Okay, so you can see that the product, if you do this first, then do this, right, you see it jump by 1. Okay, if you do that first, then do this, right, it either is neighbor or it jump by 2. Okay, so this is how they play around with the different benzene. They're going to put in different things first, put the next guy go in. Okay, remember all these things.
For the CH3 and Cl, right, how do you know which one will be like substituted inside the benzene ring?
This guy,
Yeah.
don't worry. Okay. This one I say, right, if you want to have anything Cl, right, you want anything to go in, right, make sure this is less electronegative than Cl.
Which is like almost everything.
Yeah, which is almost everything. Okay, don't be idiot and put F there. Okay,
Oh.
okay, so CH3, you guarantee that this guy will be the negative one, will join
Okay,
with the
some
Lewis
inside,
acid,
okay.
and this will be the plus come out. Okay. Okay, great. Okay, so that's about what can happen in a benzene ring, and that's all we need to know actually. Okay, I hope that didn't miss out anything. Now, so we talk about what will happen to the benzene ring. Now we talk about what will the benzene ring cause the rest. It cause the others. Okay, it depends on what group it is next to it. Okay, so if you have a group next to it, it's called it's a thing, anything that has lone pair. Okay, that's the first thing. Okay, if the guy next to benzene ring has a lone pair, okay, the lone pair normally will be in the will be in p orbitals. Okay, and then when you have a p orbitals, this is already one overlap circle. When this one also have a p, right? It will extend the cloud to here, okay, because they're all very close. So what will happen is that if you have a lone pair next to a benzene ring, right, the lone pair will also get resonance inside the ring. Yeah, so the lone pair will not be so available for other attacking comparing to aliphatic chain, not the benzene ring. Okay? Example.
You mean the chain also can react?
Yeah, no, I'm talking about what now I'm talking about how does a benzene ring affect a side branch. Just now I talked about how a side branch affects benzene ring, right? That one finished already, okay? No more benzene ring issue. Now we talk about how benzene ring affects side branch. Okay, so first thing is that if you have a lone pair and side branch, the lone pair will also try to delocalize in the whole electron cloud there. This is what we call this is called the pi plane sometimes because it's pi orbital or pi plane, because it's the plane, okay? And then they call it the extended pi plane, that kind of things. Okay? You don't need to come up with this word, but when you see this word, you don't know what it is. Okay? With this one, we call it an extended pi plane. So the whole thing is a plane. Okay? So what happens is the electron will also delocalize in the ring. Okay? The electron delocalizes in the ring, then the lone pair is not so available for anything.
What if the side branch doesn't have a lone pair?
Yep. Okay. So this will not have an issue for this. Okay. So, but let's talk about this issue first. Okay. So just example, if you have ammonia, okay, now ammonia is alkaline because of this lone pair, right? Because the lone pair, when you have water H2 comes in, you know, this lone pair will snatch H plus and dative into H, then you can kick out H minus, right? Okay, so comparing NH3, right, versus benzene ring. This is called phenylamine.
This one also got lone pair.
Yep, this one also got lone pair. So are they both alkaline? Yes, they are both alkaline, okay, because they have the lone pair, they do business with water. But point is, which one is stronger alkaline?
The
ammonia.
on top one.
Okay, ammonia is more than this. And then compare with this with the, let's say, CH3 here. What do you think?
CH3.
Which is the strongest in this three?
CH3 is like electron
Donating.
so it give. So it will make the N even more electronegative. So
Right. So this
so
is
it
strong.
is very strong.
Okay. So this is actually a stronger alkaline than this. Now understand the effect of this. It will make a lone pair unavailable. So it breaks down the lone pair. So lone pair give you what? Then you got to speak accordingly. Okay. So another example is like phenol. Okay. If anything to do with the lone pair here, this lone pair will not available if you have this. Okay. But on the other hand, right, you talk about acidity. Acidity of phenol versus alcohol, aliphatic alcohol. Then acidity is because the H plus come out and the O minus in this way, versus a strict chain, okay, a carbon and oxygens and then H plus and O minus like that, right? This is alcohol. Okay, this is benzene. Okay, so they will say that okay, which one is more acidic? Okay, obviously this is the one, because the minus sign, right, is actually a part of a lone pair, will go into the benzene ring also. Okay, so the electron on the next guy, any free electrons, will resonate inside also. So this is why the H plus will not so easily come back. Okay, so that means the stability of this ion will favor the split. Okay, so therefore this is more acidic than alcohol.
This required.
Certainly they will talk about it in the phenol chapter. Okay, but all you need to know is that the electron, free electron will be resonate inside. So what's the effect? Less available. On the other hand, this stability also increase. Okay. Okay. So what other things about a benzene ring can affect the next guy? Is carbon.
Wait, if it is electron withdrawing, then will it make the side branch extra reactive?
Electron withdrawing make the side branch. You mean the
Cl.
Cl here?
Will it make the Cl very reactive?
This one? No.
There's
Let's see.
more electrons there. As
Cl
opposite to
doesn't
what
react anything. It's
opposite to
already
what
like
you say.
plugged inside.
No, I'm talking about just now. I'm talking about how this benzene ring affect the side branch, right? So if this is the case, right, the free electron here, right, we also localize inside.
But
Right.
it's sucking it out now. Then you
You
still
have a
get-
tendency of sucking it out. Okay, so that means, right, this will not, when you have something comes to it, it will not look as negative.
But
Right.
it's sucking the electrons out.
It is, yeah, it is compensating. Okay, so when it's compensating,
Means a lot of electrons there.
but what is the chlorine's property? Chlorine's property is that
Maybe not chlorine some other electron withdrawing thing. So the side branch then react.
if this group is electron withdrawing, right,
Which will ensure that its lone pair would be outside.
yeah, but the point is that lone pair is one thing. The lone pair anyway is inside, but you talk about the electron withdrawing, right? So if this electron withdrawing, right, the idea is that the reactions is due to its electron withdrawing characteristic. Now, if I have a thing, this electron withdrawing, if the electron withdrawing power will help me to push something to this particle and it go reactions, become a new product. Get what I mean? Then that means the more I draw from this particle, I will react with this guy. Make sense? Now, we talk about different thing, okay? Just now we talk about the lone pair. If there's a lone pair issue, the lone pair are delocalized the inside, so the lone pair will not be so available. So if your reaction is due to the lone pair, okay?
You will have them.
Got it? Okay? So but in this case, right, and remember whether you have a lone pair or don't have a lone pair, right? And whether you're electron withdrawing or not electron withdrawing, right? It don't have much direct link. Okay, you can have lone pair and you are not electron withdrawing. You can have lone pair and yet you are electron withdrawing. You can don't have lone pair electron donating or yet lone pair and electron withdrawing, right? Just now we have many cases, 4 cases all out already, right? Okay? So there's no link between electron withdrawing and the issue of the lone pair itself. Okay, so let's just talk about a lone pair. Talk about a lone pair. The lone pair, if without benzene ring, is more available for other people. Now with benzene ring, it's not available for other people. Okay, so will this help you to whatever they just deduce accordingly? But let's talk about exactly what you asked is that what if the issue is caused by electron withdrawing? It means nothing to do with lone pair now. Okay, so if something which is electron withdrawing and something reactions can come out is because the X draw the A, then something like XA can form, right? Can?
But X won't be plucked out from the benzene ring.
X wouldn't be plucked out from benzene ring. Yeah, but anyway, in general, without benzene ring, the issue, okay? When you say the thing is electron withdrawing, okay, therefore it will undergo reactions, right? Okay, that means if we react with A, due to electron withdrawing characteristic, that means this one draw the electron from A, then become XA. Make sense? Now, so when this guy now,
so XA
right,
is the ionic.
I don't know, because don't have this issue, but let's talk about it. Don't worry, don't really have this issue. But let's say this guy now, right, is tag along with benzene ring. Okay? The urge of electron withdrawing, right, are greatly compensated by the benzene ring already. Okay? So therefore, right, the guy at A, right, will not look so attractive to X.
So you'll find hydrogen.
So it is why it is harder for you to react. That means this thing is not easy to react. If the issue is due to electron withdrawal, because this one like a reservoir like that. Okay? But reservoir will not let your charge to stay there for attack also. If you talk about lone pair issue. It will keep resonating. But if you're not enough, it will let you have the urge. So that you will not seek outside things and you undergo reaction. So this is why, yeah, you're right. Actually, you asked the right questions. Is that the chlorine here, right, will be super stabilized by the benzene ring. Okay. For lone pair, no issue. For electron withdrawing, no issue. That means chlorine is no longer chlorine already. So a reactive gas is no longer reactive. Okay, that case. Okay, but don't worry about it. Okay, you might not need this concept too much, but yeah, good to ask. Okay, so the second case is the first one is about lone pair issue. The second one is about carbon issue. Okay, when you have carbon next to it, okay, carbon whatsoever you have, okay, even if it is an ester whatsoever you have, there's only one thing you need to learn. It's under vigorous oxidations, okay, it will end up as a vigorous oxidation will end up as a COOH. Okay, anything with anything also. Okay, when you have a C under vigorous oxidations, it will become COH. Okay, so that's you need to know. Okay, so if without the idea is that without benzene, right, under such vigorous oxidations, right, all will become CO2 and H2O actually. But with benzene ring, right, this will always stabilize the next guy. Okay, so however you oxidize, it will still become this. Okay, so just remember, see anything beyond this. So, example, if they give you ester like that, okay, under oxidations, superoxidations. So what will be the end product? End product is 2 times of your COOH. Okay. Okay. So that's the
So
idea.
it's
Okay.
from
But
one
this side
will become 2
no, this side this one becomes COH. This side this one becomes COH. Okay.
So you kind of break into 2
Yeah, bring it to
compounds.
yeah. Okay. So just remember any C tag along with it, all will become. If you have multiple branches,
Everything will become also.
this will COH, this will COH also. Okay, so no exception. Got it? Okay, this is just another piece of things you need to know. So how many pieces of things you need to know too? What happened to the lone pair and what happened to the C when you have benzene taken along with it? Okay? Okay, so one more example. Let's have the last example before we try some other things. Comparing acidity about aliphatic acid, okay, versus a benzoic acid. No, benzoic acid. Okay, which is more acidic? Right? Which one is more acidic?
Should be the benzene one.
Reason?
Because it's years of question. My god, I just felt like it.
Felt like benzene, right? More acidic, right?
Yeah.
You're right. Okay? Benzene is more acidic. Okay. The reason is that after you form, if you first you can't see the,
It will cause COH to fully dissociate me.
it will not be fully dissociated, but relatively stronger. Reason is nothing to do with whether easier the H plus to leave. Okay. Now, a strong acid, right, always have 2 factors. Okay. The first thing is about is it easier to split. The second is about whether it's easier to come back. Okay. If it is easier to split, stronger acid. If it's harder to come back, it is stronger acid. But the dominant factor is come back. Okay, not the splitting. It's about coming back. It's like the idea is that if you this is why right, you have a HCl versus HI, right? HBr, right? Okay. We talk about HCl is more this is more electronegative one. So it's easier to have a heterolytic fission than compared to Br. So we thought that HCl is stronger acid than HBr, but it's not. Okay, in the reality that they find out the pH of this is higher than this for the same concentration.
Higher.
Okay, higher. I'm sorry, lower. Okay, pH is low. pH of this is lower than this, so it's more acidic than this. Okay, why is it so? It's because after H plus and Br minus leave, right, the H plus is more free to go compared to the H plus and Cl minus here. Okay, so there is the coming back factor, which is a dominant factor of acidity.
Oh, so it's like how easy it is to go back to it.
Yes, this is a dominant factor. Even though the first factor is a factor also.
But if it's easier to go back, then it will be harder to split also.
It will not. It might not be. It might not be. Okay. For example, right, in this illustration, okay, by the time you split, right, the issue is about the bond here. Okay. But after you split, right, the things become this. We thought that it's become this, but it's not. The actual thing is this. Resonance structure. Okay? So the idea is that when the time this one tries to draw back the time, you don't see a sharp minus at either one of O. It's spread according to O in the symmetry manner. So this structure, resonance structure will make it harder to come back compared to the easiness of split. Okay? So this one enhances the acidity of the aliphatic acid compared to anything that don't have this resonance structure. Okay? So this one, this acid is stronger than alcohol. Got it? Okay? So may not be here.
Then how come the benzene ring one is stronger?
Now, secondly, in this case, right, they are the same. Okay? It's like how easy that they fuse together is how hard that they go away, right? But the point is that if second factor is, so if they're the same factor, that means both acidity is the same. Okay, because easier to split is also harder to leave. Harder to split is also harder to come back, right? But we say that this is stronger as in this, because the coming back factor is more dominant than the splitting factor. Okay. Now, but in A level, right? A level, this one is wrong. Okay. You've got to follow your A level explanations. Okay. The A level explanations, yeah, a lot of people have been scolding the Cambridge many years till today. They still don't change. Yes, they still don't change. Okay, I record this video anyway. Okay, but just check the Wikipedia. A lot of people are saying all this already. Anyway, what happens is that they check bond energy. They say the bond energy of HBr is lesser than bond energy of HCl. Therefore, HBr is easy to split. Therefore, HBr is strong acid. But that's totally a piece of nonsense. Okay. Why is that nonsense? Because bond energy is defined as homolytic fissions, which give you back a H dot and Br dot, which is totally different from talking about HBr, right? You have a heterolytic fissions of going minus and plus. Okay. On the other hand, it makes sense because you say, right, if this homolytic fission is easier, bond energy lower, that means they're more symmetrical. So easier for homolytic fission will be automatically harder for heterolytic fissions. Okay? So actually these things we select their own mouth, okay? But in A level, too bad, follow that. Okay, why is this more acidic than this? Bond energy low. Don't say anything, get marks, okay? Happily. Check your syllabus. I know your syllabus is still 6
So they say
pages.
bond energy low, so easier to split.
Yeah, that's it. Okay, don't think too much. Okay. Okay, but the rest of explanation to follow our traditional method is the mobility of the H plus, right? Dominances. That means whether it come back. Okay, if it's harder to come back, it means that it is more acidic. That's the dominant factor. Okay. Okay. Anyway, okay. Yeah. Okay. So the idea is that when this one split, the H plus will become this. Okay. But when this one split, the time actually it give the same thing. So it's a benzene ring, and C and O here, and then dot minus here, and with H plus outside. Okay. But the point is that the negativeness, rather than spread among these two, it will resonate inside the hexagon. Okay, so make it even more harder for the H plus to come back. So this is why benzoic acid, right, is stronger than aliphatic acid. Okay, use all this concept. Okay, so remember today we learned positions, what happened to the benzene ring, okay, how you do business with benzene ring, okay, what are the positions, how to make the ring more activated. On the other hand, we talk about if you have a benzene ring, how does it affect the rest of the branch. For all the halogens, we make the halogen very stable, so no reaction at all. For double bond or lone pair or anything charged like that, it will resonate inside together. Now, on the other hand, if you have positiveness here, it will also compensate, okay, your positiveness. So if you have a positiveness things here, okay, and something will come in with a positiveness, right? It will also like a reservoir that compensate your positiveness. The electron will swim into this domain to compensate your positiveness. So positiveness will kind of spread on the whole benzene structure also.
Acid is called benzoic acid.
Sorry?
This acid.
Yeah, benzoic acid.
Then the other one?
Benzoic acid.
Ethanol acid.
It's ethanol acid, but this is benzene, anything we call aromatic. Okay, so aromatic acid. Okay, strict chain we call it aliphatic acid. Okay, so any aliphatic acid. Okay, so we talk about how now if you have positiveness, remember it also compensates your positiveness, so it will stop. It will also make it not so reactive if your positiveness is needed to react for reactions.
What's the straight chain one called?
Aliphatic. A-L-I-P-H, aliphatic. Okay. Okay, last things, do we still have time? 6, 4, 6. Of course we have time to find something. 6, 7, yeah.
7:20.
Yeah, we still have time. Okay, so let's talk a bit more. Yeah. Okay, don't worry, okay, this one later they'll talk about it in phenol chapter.
Because it's harder to rejoin back the benzoic acid.
Yeah.
Due to
The resonance structure or the extended pi plane, you just say extended pi plane, okay. Or the negative charge will also be resonated inside the benzene ring, that kind of things. Now, so last things, not last things, okay. One more thing, maybe let you feel a bit about benzene ring versus the alcohol. Okay, first we talk about which one is more reactive acid. Okay, then we say that the phenol will act as a stronger acid than aliphatic acid. Okay, so this way. Okay, this one we talk about it, right?
Acid, yeah.
Because this one compared to this one, okay, this one the
negativeness is
Yeah.
like sunk inside the ring.
yeah, okay, so it make it more stable, that kind of things. But this one is stronger acid than this one. Okay, but on the other hand, right, in the esterification, okay, we say that the alcohol can react with carboxylic acid, right? Okay, you can have this, okay, but for this is a no. Okay, we say phenol. Have you learned that actually? Okay.
Phenol.
Phenol cannot react with aliphatic acid to form ester. Okay,
Never learn it.
but it can form. But for this case, you need to use acid chloride. Okay, of course, acid chloride for this one also okay. And the way you react is exactly the same. Okay, so they will form CH3CO benzene ring versus the CH3CO CH2 CH3. Okay, they will have the same product. The idea is that this is not reactive compared to this. So that's why this cannot react with acid, this can react with acid. This can only react when you use extreme case like acid chloride. Okay? So I thought just now this is stronger than this. How come now this is not reacting with this? It depends on what's the cause of our reactions. The cause of reaction is actually the lone pair availability here. Okay? So this is okay with acid.
So the
This is-
lone pair is like already.
Yes. So you can see.
Newly
Yeah. So the idea is that don't generalize it that
Oh, it's the
phenol is
electron
more
from-
reactive or whatever is less reactive. No. Okay. You really go to what are you talking about? Okay. If it's a lone pair, the lone pair is less available than an aliphatic chain. Okay. And when it's things like this, okay, then this is stronger. Okay. So it depends on what situation you use. Okay, so that's all for benzene, I think. Okay, let's flip through your notes, see everything I covered. Two for directing, three directing, two for directing.
You still need to learn
Three, five,
how
nine.
they actually stick the second thing to the 2,4, is it?
Take the second thing to 2, 4, Z. Look, just now I teach 2, 4, 2,
Yeah,
4,
but
6, right?
we only know which stick where.
Yeah, 2 or 4 you don't know what. They are
Do we need to know what's the steps?
sorry?
Do we need to know
The
steps?
mechanism.
The mechanism
Or
is
is it
either you need a halogen carrier or you don't need a halogen carrier.
Then the rest is the same.
Yes. You add whatever, right? You either use a halogen carrier to chuck in or you don't use a halogen carrier. When
Yes.
the ring is already activated.
Oh.
Okay. Okay. So when the ring is not activated, how come they didn't teach you anything? Because you don't need to use anything. Just pour whatever you want to add.
Because it's strong already.
Yeah, so for example, if I want to check in nitro, okay, I want to have okay, I already have a phenol group, okay, I want to chuck in a nitro. Okay, you don't need to generate NO2 plus, no need, okay, so what do you need to pour? Have a good guess, okay, they don't teach, but how come I know? Okay,
Something NO2 minus.
something you're very familiar with, just pour it inside.
HNO3.
Yes. Pour it inside will do, yeah.
But you get NO3 minus. Or?
No, this will help you to pull an electrophile out. Okay, this will already help you to pull it in. So whatever the original reagent it is, so whatever you want to add, originally you need to add something else, but now you don't need. Okay, just use this. If the ring is activated. Okay.
Originally it's H2SO4.
Yeah, H2SO4 with
I
this.
forgot it. How do we activate?
How do you activate?
Yeah, how do we activate the ring?
If you already have a group of electron donating group.
Donating group.
Yeah, electron donating group. Okay.
Okay.
And electron donating group, right, is normally classified as elements have lone pair. Except one case, okay? Except one case, which is the chlorine. Okay, chlorine have lone pair, but we call it electron withdrawing. On the other hand, another exception is that alkyl group, which don't have lone pair yet, we still consider it electron donating. Okay, so many two exceptions always. Okay, and if electron donating is always 2, 4, 6 directing, electron withdrawing is 3, 5 directing. Donating is 2, 4, 6.
Actually, I see this question, I don't know how.
Yeah, sure. Yeah. First one,
Yeah.
calculate enthalpy change of hydrogenations of cyclohexene. Use the point energy we do.
How
They give you what? Delta H of
combustion.
combustion. Okay, then use combustion. Okay, good. Okay, so let's do the first one. Calculate energy change of hydrogenation of cyclohexene. Okay, cyclohexene means 6 carbon and 1 double bond, right? So hydrogenations, add many hydrogens become what can you have? I think it's just cyclohexane. Okay. Yeah, I think the number is tally also.
We will just say this one.
Yeah, the number is tally, right?
Yeah,
1
you
to
put
1 to 1, right?
hydrogen there, one hydrogen
Yeah.
there. So.
Correct. Okay. So then that is combustions, right? Right. So this delta HC of cyclohexene cyclohexene is minus 3754. Delta H conversion of hydrogen is minus 286. Delta H conversion of cyclohexane is minus 3920. Okay. So you should know the delta H is equal to minus 3754 minus 286 minus of 3920. Okay, just like that. What conclusion can you draw from this annotation and hydrogenation about the structure of benzene compared to cyclohexene? Just can you draw from this annotation of hydrogenations about structure of benzene? Oh, that means it's not a 1/3 time, is it? Something like that. Interesting. Then you go to calculate, then you get from there.
Can you draw on your hydrogenation?
Okay. So the second one is the benzene ring. So we replace the first guy. By benzene, the second guy time 3.
Benzene, we start off with a benzene already.
Okay, so it is minus 3,
Benzene plus H2.
3, 2.
Benzene can add H2 meh?
Can. And under interesting conditions, okay. That is the one is no longer your syllabus.
But
We
then
just,
how,
we just assume we can.
Yeah.
then how we know what to form?
Well, you got no choice, what you guess?
No,
Guess a wise one. Now, benzene inside have 3, right?
3.
Have 3 double bond, right?
Yeah,
You get 3, that's 3, right?
Yeah.
Okay, so when you want to open up, so either you say
Or
open one or you open all, right? Yeah, you got no choice, right?
Cyclohexene, because you have 2 hydrogen.
Right.
Yeah.
Cyclohexene?
Yeah, cyclohexene.
I
What's
thought it's
cyclohexene?
2
Of
double
course it's
bonds. 2 double bonds.
benzene is like that, right? So it's 3 of them become cyclohexane, right? You have 3 double bond here.
Okay. So we react with all the 3 double bonds.
Yeah. Either you say open all or open one, right? There's no
Cannot open 2.
no reason you want to guess an open 2. Okay. So if you open one, give you 2 double bond, it's not in the data calculus, so you better guess that open all. Okay, actually open all.
So it's two
Three.
benzenes and 3 H2.
2 benzene.
One benzene only.
But then you have 6 hydrogen.
Yeah, 6 hydrogen.
1 H2 react.
Open one double bond,
Yeah.
you chuck into, you chuck into. Okay.
So the conclusion is that benzene is more stable.
Yeah, it should be. Okay. Benzene, the double bond is more stable to open up compared to the
The
normal double
benzene,
bond.
do we draw it as a circle or as 3 lines?
Circle. Don't use that structure. Okay. But when you're thinking the time, if a circle confuses you, you can think it's a 3 line.
This is cyclohexane.
In an attempt to prepare 1 phenyl propane, benzene was reacted with 1 chloro-propane. 1 chloro-propane. Yeah, okay, and the presence of aluminum chloride under a rigorous reaction of
I think this one can. Is
Yeah, no?
divided at the back.
This one mechanism is the same thing. Why 2 phenyl propane was formed from reaction in considerable amount?
What do you mean by considerable?
That means it's a major product. 2 phenyl propane. This one, this One phenylpropane benzene. One describe mechanism for reaction prepare one phenylpropane from
Wait,
benzene
wait.
and one chlorpropane. Yeah.
If the change of hydrogenation is lower, so that means that it will give off more energy when it react. So it means that it is actually more stable.
Yeah.
Okay.
Yeah.
Which means it's stable after reacting.
Before.
But before you have more energy.
Before you have no, you're gonna times 3, no?
Yeah, I'm sure.
First one times 3? No, I mean the first number conclusion is this is one double bond, right? This inside has 3 double bond, right? You don't use this value, you use this value,
But
right?
I use the
Yes,
benzene.
this one's answer, right? This one answers. Compare with this one's answer times 3. Then you compare.
Why must I 3?
Because inside a benzene ring, inside have 3 double bond.
Yeah.
So if you want to do a comparisons, right, also make this double bond results times 3 times. This is a hydrogenation of what? This is a hydrogenation of one double bond, right?
This hydrogenation of this substance.
The hydrogenation
Three.
of
We are comparing both two different substances.
yeah, but if you want to compare, I don't think you're comparing the substance. You're comparing what's so special about benzene. Okay, that's what they want to ask. Okay. It's like you have the value for this versus the value for this for hydrogenations. But now this is a ring, right? Okay, so this doesn't make sense to talk about one double one compared with a ring. Okay, the question actually, right, okay, trust me, your teacher actually wants you to see into something, which is what if I open up 3 times of this double bond?
So if
comparing, we're opening a ring versus 3 times of a double bond.
So if it times 3, right, which is the theoretical benzene
Yes,
structure,
correct.
then the
You realize that
H
benzene is different,
will be lower than actual.
lower than totally overall is exothermic.
Yeah, both are exo.
Both are exo. So
Which is
so this time 3 structure, and the conclusion gonna say this is more stable,
So
more
stable
stable
means
more
low,
exothermic.
low and then
lesser
lower-
exothermic
Yeah,
when you
lower.
open it up.
So it means this value times 3 the net.
Yeah.
This one, the cyclohexane.
No. Your answer times 3.
Answer times 3.
Your answer is the energy involved in opening one double bond, right? Yeah, so minus 120 times 3 minus 360. So you release more energy than minus 206. But that means benzene ring actually, if you open up all hydrogenations, right, will give you lesser exothermic because it's actually more stable structure. Oh, not considerable amount. I think this case is a minor amount. That means you have some. Why is there a sum of the 2 phenylpropane will come out?
considerable means
Some amount, considerable amount. Okay, but it depends on the question. It says the considerable amount is a big amount or considerable amount is a small amount. But it's a considerable amount. Okay. Why we're talking here?
you're supposed to be big.
But according to the question, this is not main product, right? The main product is 1 propyl.
Means not very small lah.
Not very small. That means you really have some. Okay, so this is the. What did they do? They do this with chlorine, right? Chlorine.
Benzene was reacted with 1 chloropropane in the presence of aluminum chloride.
Okay. So in the presence of aluminum chloride, CH2, CH2, CH3 will come out.
Aluminium chloride is
Aluminum chloride is
Cl Cl
it's a Cl and
AlCl3.
yeah, it's a Cl with the covalent bond absorber. Okay, so this is the guy that left alone. So
The whole thing below is a plus, right?
sorry,
The CH2, CH2, CH3.
the plus is here. It's at this carbon.
Oh.
Right, you got one hydrogen less, right?
No, you don't have one hydrogen less. You have like one chlorine less.
Okay, yeah. So plug it in, you have one phenol of this. Why do they say you have some amount of two phenol propane
When you
is
plug
this?
in a hydrogen, you can kick out.
Yeah. I don't see why, unless the chlorine is here. Victorious
You
reaction,
do
okay.
activity 1 3 already.
Yeah, it's easy. Activity is MCQ.
No, activity 1 you write a lot.
No need, I wrote like from here to here.
Huh? Isn't it a full DRQ?
No,
It's not a full DRQ, man.
maybe it's somebody really care.
Then the P and C
Actual question I do it.
assignment, you know, do question 4.
Don't know. But actual question I how to know.
Assignment you know do all meh? The last question of assignment.
I thought it was quite okay, maybe I don't know how to do one.
You let me see, I don't know how to do that.
Okay.
I don't know how to answer your puppy. Any answer you have?
Maybe it's in Google.
Yeah, maybe. This is how come we can switch the position like that? Yep, no info, okay.